So the first problem that I have on hand, let's see, y triple prime. First time we're doing this, triple, the third derivative in these equations. So just goes to show how far we have come. Now, not plus actually, it's minus. Minus 6y double prime, 6y double prime plus 2y prime plus 2y prime plus 36y is equal to 0. We need to find the general solution of that. So first thing first, let's write our characteristic equation. That's just gonna be third derivative. It's gonna be m cubed. Minus 6 the second derivative we have m squared. This process is the same as before. I don't know this. I'm actually recording this video in bits. Actually, I did mention that. Yeah, your the derivative order, replace that with m to the power of the derivative order. Anyways, I did mention that. Anyway, so now back to topic. Minus 6 m squared plus 2, it's the first derivative, so just m to the power of plus 36. Y don't need to replace that with anything, or just 1 really. So plus 36 equals 0. Now there's something really important I need to say, and I actually have said this a bit before, but in general, for solving differential equations in differential equations course, and whenever we encounter something, we need to find like some solution of some bunch of simultaneous equations, or solve some polynomial. Those are not exactly the primary goals of our course. Okay, that's why we just leave those to the calculator. Okay, so that's what we are gonna do. Okay, so anything algebraic, we're just gonna leave it to the calculator. So let's see. This is actually third degree polynomial. So let's see, third degree. Now the coefficients are 1, minus 6, plus 2, and 36. 1 minus 6. Okay, so 1 minus 6. So minus 6 plus 2 and 36. Okay. So let's see if it works out. So the roots are negative 2, 4 plus square root of 2i. It's good that it was able to express that exactly. And then you have the conjugate, right? Yeah, so 4 minus square root of 2i. Okay, and all of these, there doesn't seem to be any repetition. The calculator would have told me otherwise. So the three roots are, and actually you can only have three roots here. It's third degree polynomial. So three roots are m equals negative 2 and 4, and 4 plus or minus square root of 2. Actually, it's not 2i. Let me just make sure. So you have negative 2 and 4 plus or minus square root of 2. Now, how are your solutions gonna look? Actually, this is not too difficult if you even just come with the basics from the second order differential equations. Just need to use those forms. So we have one distinct real solution for that. Okay, so a general solution, okay, it's gonna be something like this. So we have one distinct real root. For that, you're gonna have some constant c multiplied by e to the power that root, okay, and then x. Okay, so that one's done. For a complex root, what you're gonna have, the real part of that is 4, so e to the power 4x. I'll keep that outside. Inside, you're gonna have the trig expression. Okay, that trig expression. So let's say some constant c2, multiplied by cosine of your imaginary part multiplied by x. So square root of 2x, and the same thing with sine. So some again some constant. I'll call that c3. Okay, and that one is multiplied by the sine term. That one is multiplied by sine of square root of 2x. All right. So I actually should have used square brackets. But anyways, this is how you find the solution. This is we have very easily solved a third order linear homogeneous differential equation constant coefficients. Just need to see as you can see, it's all of these. As long as you can find the roots of the characteristic equation, which sometimes obviously if your degree your polynomial degree is too high, or you obviously wouldn't be able to now. But as long as we can, it's pretty simple. Find all the roots, and according to this table, according to what we have learned so far, just use the forms. According to what our roots are. Okay, so let's do another problem. What we have here is I'll make sure I copy this correctly. It's pretty big. So it's with the calculator I'm currently using, it's as big as you can get, because it's a sixth order differential equation. You'll rarely encounter these, I think. Now, y, sixth derivative plus 4 times this plus 22 times the fourth derivative plus 72 plus 72 times the third derivative plus let's see, um, 153. Okay, 153 multiplied by the second derivative plus 324 multiplied by the first derivative plus just 324 plus, no, not just 324, that I do make that mistake quite a lot, but anyways, 324 multiplied by y cannot have any constant term in the equation at all. Okay, otherwise it wouldn't be homogeneous. All right, so all of this is equal to 0. Now we again, just like before, we need to first write our characteristic equation. Is, we have the sixth derivatives of m to the power 6 plus 4 m to the power 5 plus 22 m to the power 4 plus 72 m cubed plus 153 m squared plus 153 m squared. By the way, this might not need to be mentioned, but we really need to be careful that we place the corresponding powers of m, for the derivatives here. Suppose say, just say that this term didn't exist, the y prime term didn't exist. We really need to be careful about that we don't write 324 to the power m. Like, don't expect all the derivatives, okay, within your highest order, okay, or the order actually of the differential equation. Don't expect all of them to exist, or all of them to have non-zero coefficients. They might not. Okay, the y prime term here, the y, the fifth derivative here, they might be absent. We need to be careful that we don't make a mistake in the characteristic equation. That aside, all of these here do in fact have coefficients. So 324 y prime, so that's just m plus this. So this is, all of this is gonna be 0. All of this is gonna be 0. Again, this pretty much impossible for us to solve by hand. At least it's gonna take a lot of time. So I'm gonna plug all the coefficients in my calculator. So let's see, 1 4 22 72 1 4 22 72 153. Then we have 324 and 324, right? Yeah, so 324 again. All right, so the roots are, okay, so you have negative, these numbers on the right side, these are the multiplicities, or how many times the roots are repeated. So negative 2, that's repeated 2 times. 3i, that's also repeated 2 times. And naturally the conjugate of that, negative 3i, is also repeated 2 times. So I'll actually write those down. So you have actually different color. So you have let's see, m equals negative 2. Okay, and I'll write a small number here, so it's repeated 2 times. Okay, and I'll just write plus or minus 3i, and this is, the whole pair is repeated 2 times. Okay, that's what matters. The whole pair is repeated 2 times. Okay, now how do I find the general solution? Okay, how do I find the general solution? Well, let's just use those forms of ours, what we found. So if you have the first thing, it's a this one is a repeated real root. Okay, it's a repeated real root. It's repeated 2 times, and really, since it's just repeated 2 times, that's, the form is, you don't even need to see it from there. It's exactly the same as what we did with the second order DE. So why? Okay, so from here, this the portion of solution from here is gonna be, let's see, so repeated 2 times. So you're gonna have some general linear term in x. So c1 plus c2 multiplied by x, and then this is multiplied by e to the power that repeated root, so negative 2, and then you have x. All right, so this is that portion. And for the other part, what we're gonna have, okay, so this pair is repeated 2 times. So again, we could actually, there's a couple of ways to do this. We could use this form right here, write them separately on, and also write them separately on. But if we want to write it in the most concise way, we can just refer to this. So It's going to be e to the power lambda x. So lambda is, the real part of the root. Interesting here is we saw, it's 0 plus or minus 3i, right? 0 plus or minus 3i. So this is 0. This is 0. It's e to the power 0. That's why this is going to be 1. So this factor, for this solution, this factor doesn't matter for now. All right. So what you're going to have is only these cosine and sine terms inside. So, since it's repeated twice, so k is equal to 2. Okay, k is equal to, so you're again, gonna have a general linear term, so up to x to the power 1. Okay, that's, then multiplied by cosine, and a similar general linear term multiplied by sine. So that should do it. We should have 4 arbitrary constants for this. That seems like what will happen. So what you'll get here again, I'm just ignoring the e to the power 0 because that's just 1. Now inside, what I'm gonna have, these things are gonna be some constant. I'll call that c3, just going in order, plus some constant c4 multiplied by x, basically a general linear term multiplied by cosine of mu x. Mu is our imaginary portion, right? Mu is our imaginary portion for this root, so which is 3. So cosine of 3x, and similar for sine. We just need to be careful that the constants are not the same. Okay, so it's let's say it's c5, okay, plus c6 multiplied by x sine of 3x. All right, so this is my solution. This is my general solution to that 6th order linear homogeneous differential equation. And this is probably I personally hope that you don't even face this 6th order equation, because these are usually tough to deal with, especially if you cannot solve the characteristic equation simply. But this is probably as far as you'll go if you're just given question like this. Otherwise, special circumstances, you might be told what are the roots and all. But anyways, this is as far as it should go with these equations. So now we know, in at least in theory, how to solve any nth order linear homogeneous differential equation with constant coefficients. It's a different matter whether you can solve the characteristic equation or not. But anyways, we at least know how to. So that should be the end of this video. That should be the end of everything I had said. So if you like this video, please do leave a like, please subscribe, and yeah, so keep studying smart.